Okay, so now let's discuss chapter 2, water, the solvent for the biochemical reactions. And then there are 5 different topics. So water's polarity, hydrogen bond, acid, bases, and pH, titration curve, and buffers. Okay, so basically the atom with incomplete valence shell can share or transfer valence electron with certain other atoms, which we discussed in the chapter 1. Okay, and these interactions usually resulted in atoms staying close together, held by attraction called chemical bonds. And a covalent bond is the sharing of pair of valence electron by 2 atoms, which we discussed in the chapter 1. So in the covalent bond, the shared electron count as part of each atom's valence share, right? So like the hydrogen atom, right? So you have their valence electron 1 and 1, and they share this one pair, okay? And that's a hydrogen, okay? And can have a single bond, double bond, and triple bond, okay? Depending on how many pairs of the electron are shared, okay? So for example, in here, the hydrogen, 1 pair of the electron are shared, so you have this single bond. The oxygen, all right, the oxygen, they share 2 pairs, so you have double bond, all right? And the water, you share 1 pair, 1 pair, and then you have a single bond here. And the methane, so you share 1 pair. The carbon share 1 pair with each of these 4 hydrogen, okay? And then also we talk about the electronegativity. Basically, that's the ability of the atom to attract the electron in a covalent bond. And from the upper right, they have the strongest electronegativity, like oxygen and fluorine. Okay, and then the lower left, they have the lower electronegativity. Okay, then so the nonpolar covalent bond, basically that means the atoms shared the atoms share the electron equally. That's nonpolar covalent bond. And then in the polar covalent bond, one atom is more electronegative, and then the atom do not share the electron equally, and they share unequally. All right. So like here, the polar bond. All right. So electron. This is the structure of water. So the oxygen has a partial negative charge, and the hydrogen has a partial positive charge. This is because they have the uneven distribution of the electron, all right? Because oxygen has a higher electronegativity, and the hydrogen has a lower. And then electron basically will be closer to oxygen than the hydrogen. Therefore, the oxygen will show a little bit negative, and hydrogen a little bit positive. Okay, because electrons are unequally shared. Okay, and this we call the dipole moment. Okay, dipole moment. So we have more negative here and more positive here. That's dipole moment. Okay, so this the fluorine has the highest electronegativity. All right, and then oxygen, nitrogen, sulfur. These are all strong electronegativity. So are the polar bond molecules. So the molecule, like the carbon dioxide, they have a polar bond, but given their geometry, are non-polar molecule. They have a 0 dipole moment, all right? Because this is geometric distribution, so they have zero dipole moment. Although the carbon will be more positive, oxygen more negative, but that because of this structure, they show the zero dipole moment. And here we have a dipole moment because we have oxygen negative here, positive here. All right, that's a water. So the ionic bond, that's held by the positive and negative ions. The salt bridge, that's attraction occur when oppositely charged molecules are in close proximity. That's salt bridge. The ion dipole interaction, when the ion in solution interact with molecule with dipole. So that's ion dipole interaction. So that means, for example, the potential chloride dissolve in water because water, right? They have the potassium chloride is the ion that dissolve in the solution of water, all right? And that the water has a dipole moment, all right? Water has a dipole moment. Therefore, they have this ion dipole interaction, okay? The van der Waals force, that's bond that do not involve the electrostatic interaction, that's a van der Waals force. The dipole-dipole interaction, that's the force occur between the molecule with dipole, one positive and one negative. So the example would be the two water molecule, dipole-dipole interaction, okay? And dipole-induced dipole interaction, that's weak and generally do not lead to the solubility in water. That's dipole-induced dipole interaction. The ionic bond, so transfer of an electron from sodium to chlorine, that's the sodium chloride, that's the ionic bond. A charged ion is called an ion. So cation is a positively charged ion, and ion is a negatively charged ion. So the ionic bond is an attraction between an ion and a cation. All right, that's ionic bond. And this is the ionic bond become replaced by the ion dipole interaction. So when you have this sodium chloride, right? Sodium chloride dissolve in the water, right? Sodium chloride dissolve in the water. Then that give you the ion dipole interaction. So the ion is from the sodium and the chlorine, and dipole is from the H2O. So this is hydrogen. Hydrogen will have the interaction with chlorine. And then oxygen here, oxygen will have the interaction with the sodium. So this is a typical ion dipole interactions, okay? Ion dipole interactions. So this is ion dipole interactions. So this is the ion, okay? The potential chloride dissolve in the water, and that gives you the ion dipole interaction. And then when you have an alcohol or ketone dissolve in the water, all right, and then you have this dipole-dipole interaction. Okay, dipole-dipole interaction. So this like this alcohol OH, all right, the functional group here OH, and then this positive interact with the oxygen negative, all right, and this negative interact with the hydrogen positive. So this is the typical dipole-dipole interaction of polar compound. And the dipole-induced dipole interaction. So this is the typical dipole-induced dipole interaction. Okay. So a polar molecule like water can induce a dipole in a non-polar molecule like the oxygen. All right. So so for example, the oxygen. All right. So the oxygen and water. So basically, this is non-polar molecule. Then this dipole molecule, all right, the polar molecule, they can induce a dipole, all right, because this oxygen is negative, all right, and then they can induce a dipole. So be positive on one side, negative on one side. So this is an example of a dipole-induced dipole interaction. Okay. And then the induced dipole interaction, or the London dispersion forces. So it's a momentary attraction and the repulsion between the nuclei and the electron create the induced dipole and lead to a net stabilization due to attractive force. Okay, so that's the induced dipole and the induced dipole. So you have two nonpolar atoms or molecule, right? And then you have momentary attraction, right? So attraction and the repulsion between the nuclear and electron in neighboring molecule that will lead to the induced dipole like this. Okay. And then the example will be this, all right? So upon the cooling, they form the solid. That induced dipole interactions. They have biochemically relevant bonded energy, all right? So covalent bond, see the energy, covalent bond is the highest. And then the ionic bond, all right, in the middle, all right, below the covalent bond. Then you have the ion dipole energy, the strengths, all right, and then hydrogen bond. And then the lowest bond energy is the van der Waals interaction, all right? So a covalent bond has the highest strength, then followed by the ionic bond, then the ion dipole, hydrogen bond, and then van der Waals interaction, all right? That's the strength of bond, okay? The solvent properties of water. So we have the hydrophobic, hydrophilic. Hydrophilic, that means the water loving, can dissolve in water. Hydrophobic, tend not to dissolve in water. Amphipathy, that's a characteristic of both hydrophilic and the hydrophobic. Okay. So for the hydrophilic, the polar covalent compound, alcohol like ethanol and the ketone, and sugar, ionic compound, amino acid, phosphate ester. Hydrophobic, we have nonpolar covalent compound. Okay, fatty acid, cholesterol. Okay, these are hydrophobic. And then the amphipathic molecule that both, because have both polar nonpolar character, and interaction between nonpolar molecule is very weak. That's the van der Waals, right? The Michel, that's the formation. The Michel is a spherical arrangement, like this spherical arrangement of organic molecule in water solution, classed so that their hydrophobic part. Hydrophobic would be buried inside, like this, buried inside, and then hydrophilic would be on the surface of a sphere in contact with the water environment. Formation depends on the attraction between the temporary induced dipole. Okay. The hydrogen bond, basically this attractive interaction between the dipole when positive end of one dipole is a hydrogen atom bound to an atom of a high electronegativity, like oxygen or nitrogen, all right? The negative end of the other dipole is an atom with a lone pair of electrons, like oxygen or nitrogen. And the hydrogen bond is non-covalent. Okay, so like this, there's hydrogen bond between this oxygen and the hydrogen. Okay, oxygen and hydrogen. This water, they form this hydrogen bond, right? Hydrogen bond, right? Or this here hydrogen bond between the hydrogen and nitrogen, hydrogen and the fluorine. So each water molecule can be involved in a 4 hydrogen bond, 2 as donor and 2 as acceptor, right? 2 as donor, 2 as acceptor, right? So that here, this hydrogen is a donor, right? Donor. And this oxygen here is the acceptor. And here is a donor. And here is acceptor. So the maximum, you can have 2 donor and 2 acceptor, all right? And that give you this tetrahedral arrangement of water molecule. So even the hydrogen bond are weakened than the covalent bond. They have a significant effect on the physical property of the hydrogen bonded compound. So basically, you compare this water, ammonia, methane, and then you can see they have similar molecular weight. And then you can see the melting point, boiling point is much, much higher than the ammonia and the methane, all right? Because they have a hydrogen bond. Each water molecule involves 2 as donor, 2 as acceptor, 4 hydrogen bond. So that's why it's more stable than the ammonia and the methane. Okay. And the water, that's the hydroxy group of an alcohol and the water, all right? So the hydrogen bond acceptor, this is donor, okay? And the carbonic group of a ketone here, all right? And the hydrogen is a donor, all right? And then oxygen here is the acceptor. The amino group here, hydrogen is the donor, oxygen is the acceptor, okay? So the hydrogen bond thing is important to stabilize the 3-dimensional structure of biological molecule like the DNA, RNA, and protein. Okay, so for example, the hydrogen bond between the double helix DNA, all right, and also the hydrogen bond in the secondary structure, tertiary structure of the protein. They can stabilize the structure. Okay, so this is the secondary structure, all right, stabilized by this hydrogen bond, and also here for the tertiary structure, the hydrogen bond here. Okay, and then the next topic would be this acid, base, and the pH. So acid, which is a molecule, behave as a proton donor, all right? Proton donor will be acid. The base will be proton acceptor, right? The proton acceptor will be the base. And then the AC strength, all right? So basically, we can derive a numerical value for the strength of an acid, all right? And that's described by the Ka, all right? So from the acid, all right? And then the A minus, A negative, and hydrogen here, all right? So this acid, and then you have a conjugated base, right? Conjugated base, all right? And then the Ka will be the multiplication of these two the concentration of these two over the concentration of the acid. All right. So if it's the correct way to write this. Yes, Hadeo.
So are we gonna have like numbers with the concentrated acid so that we can calculate the concentration? Or how is it gonna be exactly? I know I stepped like a step forward, but like how is it gonna be exactly? And what if we have like two like more complex than this one? How are we gonna use it?
Yeah, we will explain that in the next few slides, all right? Just a second, hold your question until the next few slides. If you still have a
Okay.
question, then you can ask me again, all right?
Okay.
So basically,
Sorry.
this is Ka. Oh, no problem, don't worry. Yeah, so this is a correct way to express these equations. So it's Ha plus water, all right? And then the A negative, that's conjugate base, all right? Acid conjugate base, and then base conjugate acid. Okay, and then Ka expressed as this way, and then let's go to next slide. This is just the ionization water, and then the pH. So basically, pH is negative log of a H concentration, right? And the Ka, so as we remember here from here, Ka is a multiplication of Ha over the Ha, all right? So Ha. So if you take a log on both sides, all right? You take a look. See from here to here. You take a log on both sides, all right? So you put the log here, a log on Ka. So it give you the log P, log Ka. And then you have log H, all right? Plus log of these two. So that give you these two, all right? All right, so that give you these two, all right? So you have log H plus log this ratio. Therefore, the negative log H, because you move this one to this side, to the left side, so that become negative log H, and then move this Ka to the right side, will be negative log Ka plus log A negative over the Ha. And then negative log H will be pH. Negative log Ka will be pKa. Therefore, the definition of pH and pK will be pH equal to the pKa plus log A minus over the Ha. All right? Do you understand this so far for this equation, for the, the relationship between the pH and the pKa? So pH equal to the pKa plus log conjugate base over the acid. All right. So remember the pH, right, equal to pKa plus log A negative over Ha. So which will be the conjugate base over the acid. All right. Over the acid. All right. So this conjugate base over the acid. And so that will be pH equal to the pKa plus log conjugate base over the weak acid. So we can see from this equation. So the concentration of the weak acid here and the conjugate base, when these two are equal, all right? When these two are equal, then pH will equal to the pKa. If the pH smaller than pKa, all right, smaller than pKa, so that means this must be negative. If this is negative, then that means the weak acid will be the predominant, all right? Then this will be smaller than 1, and then this will be negative, all right? So that's when pH smaller than pKa. If the pH is greater than pKa. That means the conjugate base will be predominant. And this ratio will be over greater than 1. All right? Greater than 1. Therefore, the pH will be greater than pKa. All right? And this is just to show the titration. The experiment to measure the amount of acid are added to measure the amount of base. All right? And so you can see the change of the pH curve. But we will come to here first to show you the calculation. To calculate the relative amount of acetic acid and the acetate ion present at the following point when 1 molar of acetic acid is titrated with the sodium hydroxide. Also use the Henderson-Hasselbalch equation, which is this equation, right? Henderson-Hasselbalch equation, okay? And then to calculate the value of pH at this point. So basically, the acetic acid and acetate ion, this is weak acid, and this is a conjugate base, all right? Conjugate base. And then in the beginning, you have 1 molar of the acetic acid, all right? And now, let's say if you add 0.1 molar of the sodium hydroxide, the titration, right? Then add 0.1 molar of sodium hydroxide, and then what will happen? Okay, so what will happen? Do you need me to go through this equation to do the calculation? Hello? Okay, good. All right, so I will demonstrate how to do this quickly. I'll try to do that on the PowerPoint slide. If not, then I will show you my whiteboard. We can do that on the whiteboard, okay? So first of all, okay, so first of all here, so here, so we have us, okay,
I can't see that. Would you be able to write it
in the
for me?
whiteboard.
Yeah, that would
Okay,
be
all right,
helpful
so
for
I'm
me.
going to turn on my video, okay, and then I will show you on the whiteboard, okay,
Okay, thank you, Professor.
no problem. So, all right, so sorry, can you see my writing on the whiteboard?
Yes.
Yeah, we can see it.
Yeah, we do.
All right, acetic acid, all right, so we have this acetate ion, all right, okay, so in the beginning, we have 1 molar, all right, 1 molar here, acetic acid, and remember, it's a weak acid, all right, and then we have the conjugate base here, all right, so the conjugate base will be here, and the acetic acid will be here, okay, near bigger. Write a bigger, just a second. Okay. Okay. This here will be acetic acid, okay? And then this will be acetate, the base, okay? And then in the beginning, you have the 1 mole of the acetic acid, okay? And now you're going to titrate with sodium hydroxide. So that means if in the first case, if you have 0.1 mole of the sodium hydroxide, okay? So that means you will consume, you will make this go this direction, all right? So it will be 0.9, all right, 0.1 and 0.1, because this 0.1 will need to be used by the sodium hydroxide.
Hi, sorry, I just asked some students in the class something. You're good though.
Oh, okay. All right, so that means that if you have 0.1 mole of a sodium hydroxide, that means you need to go this direction, all right, to give 0.1, 0.1, so that this 0.1 of the hydrogen can be used for sodium hydroxide, all right? So therefore, the pH, I will use the blue one, all right? The pH will be pKa plus log, okay? The acetic acid will be 0.9 in here. And then acetate ion will be 0.1. All right, so that would be the answer. So that'll be, you have to calculate the log 0.1 over 0.9, and then plus the pKa. That give you the pH. And then again, if it's a 0.3 mole, if you use a 0.3 mole, all right, if it's 0.3, so that means if it's 0.3, then here will be 0.7, 0.3, 0.3. All right, then the pH is pKa plus log. The base is 0.3, and then the weak acid is 0.7. All right, so this is the calculation you have to calculate. Yes, what's the question?
So for over here, it says it's 1 mole, right? And then
1 mole, yeah, in the beginning, 1 mole of acetic acid, right?
yeah. And then how did you know that this is 0.3 and this is 0.3? Like
Oh, yeah, because the weak acid, all right, have to dissociate, all right, dissociate. So dissociate weak acid to the conjugate base and then hydrogen ion, and then the sodium hydroxide. So the amount of this side depend on the amount of sodium hydroxide you added. If you add 0.1 mole of the sodium hydroxide, all right, because it's a strong base, so that means you need to have the equal amount of hydrogen to neutralize it. All right, so if you have 0.1 mole of the sodium hydroxide, then you need the 0.1 mole of the hydrogen. Then this will be 0.1, and then this is 0.9. All right.
okay. But isn't this if it's 0.1 plus 0.1?
No, because you have 0.1 to dissociate, and
yeah.
these two combine is 0.1. All right, it's like this CH3COOH, and then CH3COO negative plus H plus. All right, do you see this?
Yeah.
Okay, so that's the idea. So if you dissociate 1 molar here, then if you dissociate 1 molar, that means each of these will get 1 molar.
Okay.
All right.
But
So
then
then
does it dissociate again? Will it dissociate again or no?
say that again. Oh,
So
will they dissociate again? No,
yeah.
this is a conjugate base already. So they will, this just, they will come to the equilibrium, all right? Just between these two sides.
Okay.
They cannot, this acetate ion cannot dissociate further,
Okay.
all right? So basically, based on these Mona, just a second. So based on these idea, then you will be able to calculate the pKa, all right, and calculate the pH, all right, because pKa for each weak acid, they have the certain pKa, and all you need to do is to calculate the pH. Yes, Mona, what's your question?
So for the third one, like 0.5, it's gonna be 0.5 for acetate and H plus both,
Yeah, if it's 0.5, okay, so then it'll be 0.5 and 0.5,
and
all
acetate.
right? And then the log, that'll be log 1. So log 1 is a 0. And at this time, pH will be equal to pKa.
Yes. Okay. Thank you. Got it.
Professor, how did you get to the 0.5 for the acetic acid? I mean the weak base. The weak acid, I
Point
mean,
5,
sorry. Yeah, how
you
did you
mean?
get that? When you just get this, when you
That's
did this
the,
example.
that's the under the condition when you add 0.5 mole of the sodium hydroxide. If you add 0.5 molar, so that means you need to have a 0.5 molar of the hydrogen ion here.
Yeah,
So that means you have to dissociate 0.5. When you dissociate 0.5, then you get 0.5 here.
but if I'm just, so if it isn't it 0.5 over 0, oh, okay, I get it now. Okay, I got it. Okay, sorry. Thank you.
Okay, no problem. Good. So that's how you perform the calculation for this kind of question, all right? When they have an equal amount, they say the weak acid and the conjugate base, when they have equal amount, then the log will be 1, log 1, now be 0, okay? Here will be 1. The ratio is 1. When the ratio is 1, all right, the log 1 will be 0, and then the pH equal to the pKa. All right, so that's the Henderson-Hasselbalch equation to calculate the pH, okay, for the weak acid and the conjugate base. Okay, so now let's continue. And then the titration curve. So basically, so the equivalence point, the point, the acid base titration, enough acid has been added to exactly neutralize the base. So that's the equivalence curve, okay? A monoprotic acid release 1 hydrogen per mole. Diprotic acid release 2 hydrogen per mole. And triprotic acid release 3 hydrogen per mole. And this is just the relative abundance, all right? So acetic acid, and then increase the amount of the acetate ion, equivalence of the hydroxide added, all right? And here the pH equal to the pKa, all right? When the weak acid equal to the amount of the conjugate base. And then you can see that the change of the pH is very slow, right? It's very tiny. And the buffer, so that gives you the concept of buffer, the idea of buffer. So if you don't have the buffer, like this unbuffered water, if you add 1 mole of the hydrogen chloride, then the pH drops significantly. However, if you have a buffer, when you add pH, you add the strong acid, then the pH will not change dramatically. And so as these strong base, sodium hydroxide. Okay, if you have buffer, then they don't change the pH dramatically. And so that the buffer basically have weak acid and conjugate base. All right, and so that'll be this example. All right, that give you the buffer. And so how do we choose the buffer? That basically between the pH and the buffering capacity for the ionic environment needed for the biological sample being studied. That's how you choose the buffer. And the buffer range is effect in the range of about plus minus 1 pH unit of the pKa of the weak acid. All right. So basically, pKa equal to the pH, right? Equal to the pKa. That's 1-to-1 ratio. Okay. So if it's a 10 times, all right, if a 10 times ratio, so they say the base over the acid. So the acid is 10 times more than the base. The pH will change 1, all right? And then if the base is 10 times more than the acid, then the pH also change 1. So this is just to show you the buffer capacity. Do you understand this concept? So if I use this whiteboard again, all right, use a whiteboard again, okay. So the pH equal to the pKa, so that's when the weak acid and the conjugate base, all right, it's a 1-to-1 ratio, okay. pH equal to the pKa, all right, because the log of 1, that's 0, okay. And now, if the acid has 10 times more, if you have 10 times more than the base, right? You have 10-to-1, therefore the pH would be pKa, all right, plus log 0.1, all right? Therefore, the log 0.1, that'll be pKa minus 1, okay? And now, if you have 1 acid and 10 times a conjugate base, the pH will be P equal to pK plus log 10 over 1, all right? 10 over 1. Log 10, that'll be 1. So that'll be pKa plus 1, all right? So that means even if you change the concentration 10 times, the pH will only change 1, okay? So if you change 100 times, then the pH will change 2. So that's the buffer range. Okay, any question? Very good. So the buffering capacity is related to the concentration of the weak acid and the conjugate base, all right? So that's buffering capacity. That's what we just explained here. If you change the concentration 10 times, then the pH will change only 1, okay? On either way, okay? And so that's why you can see this buffer. It's very important for our living system, all right? So that we don't change the pH dramatically. So these are some naturally occurring buffer, all right, which is important. So to select a buffer, you need to have a suitable pKa and not interference with the reaction or detection of the assay, suitable ionic strength, suitable solubility, and non-biological nature. And so these are the commonly used the buffer in the biochemistry laboratory. So like the trees, all right, the pKa is 8.3, and TS is 7.55, the HIPS 7.55, MOPS is 7.2, the PIPES is 6.8. So basically you choose the buffer according to your need, all right? So so that's how you choose the buffer.